Hello, welcome to the lecture on linear programming. We will start by recapping what we had done before. So, can you remind me? We were looking at linear algebra, right? And the important things which we want to remember is what is linear independence? We are given a bunch of vectors in a vector space. What is linear dependence? What is linear independence? And all of you know it, right? That is fine. And then once we have this concept, then we can talk about columns of a matrix as vectors, and then we can consider their rank, which is the number of linearly independent columns, or the dimension of the span of those columns, or the dimension of the span of the rows. Multiple ways we can say what is the rank of a matrix, right? And then the third thing which kind of allows us to calculate or compute these things was Gaussian elimination. And I think this is a nice thing to know in general, not just for this course, because there is a very strong tool. It actually tells you how your solutions of Ax equal to b or Ax equal to 0 looks like, right? So, what are the possibilities for Ax equal to b? There can be no solution. When will that be the case? When b is not in the column space or span of the columns of A, right? Otherwise, there could be a unique solution, and unique solution will happen if rank is full, rank is n. That means every vector can be uniquely represented as a linear combination of my column vectors, right? And then if the dimension spanned is less, but b is a vector, then it turns out that I will have a large enough space which is going to be the solution. And that can actually be described by Gaussian elimination. Some of the variables will be free, some of them others can be written down in terms of the free variables, right? So, can you think of how this space will look like? Can you tell me, let's say in 2 dimensions, let's say I have 1 degree of freedom, then my solution space will be a point, square, line. It would be a line, right? It would be a one-dimensional space. That's what I want to emphasize, right? It's not a set, like a bounded set. It is going to be a space. Okay, good. Now, I want to give you a slightly more detailed introduction of linear programming. Before we go further, we will kind of see that this linear algebra which we have seen is not good enough to give us a solution. We need to know this, but this is not good enough for solving linear programs. Okay, but before that, let's get acquainted with linear programming more. Okay, remember I told you the standard form is such that equality constraints and x greater than equal to 0, right? I told this and you accepted it, but now since you accepted, I will ask a question. What does it mean that this is the standard form? And now I need a mathematical definition, right? Not the English definition of standard that I am familiar with. So I said standard form of linear program. You said wonderful, it is a standard form. But what did you get out of it?
Everything can be reduced into this.
Okay, good. Everything, you mean to say can be reduced depending on your preference. Correct? What does this mean? Reduced. You have 2 set of linear programs. Linear program A, this is an optimization problem. B, this is another optimization problem. What does it mean that A can be reduced to B? Now, see, it's great. That is how mathematics works, right? You have some problem, you formalize it. And then the next step is, oh, I can probably solve it like this. Then you have some intuition behind it. So this is the intuition behind it. But then you need to formalize it because we are mathematicians, right? We are not biologist, chemist, or whoever you want to, insult, right? So, so since we are mathematician, we need to formally make sense of this. Very good. So it has to be something like solution of A mapped to solution of B, and once again you are creating new terms, and I will keep asking what map to means, but then we will describe. But now we are getting closer and closer, right? Map seems much more mathematical as compared to there is a function or there is a process by which I can take a solution of A and convert it to solution of B. This was enough. It was just a problem, but since this is an optimization problem, we have to take care of the, is it enough that solution of A is solution of B? There is a process, let's say, or a function, but is that enough? Okay, so yeah, that will depend on whether you want the arrow to be this way, or this way. But A also has an objective function, right? So the solution of A should map to the solution of B, and right, because why are we doing all this? The reason is that instead of solving A, we will just solve B. So somehow the idea is, oh, the optimal solutions of A should map to optimal solutions of B. And vice versa if you want to say that they are equivalent or something, right? Okay, good. So that is the plan. That's what we want to kind of formally define and show that this is our standard form. But before I do this, I need to talk about what could linear programming be, right? So linear programming is linear constraints and linear objective function, right? So it is min slash max C transpose X such that all these kind of constraints could have been possible. All of them, yeah, so they seem linear, right? And remember, x greater than equal to 0, I can represent it as this, right? So these are the kind of possible linear constraints I can put. Okay, and let's take some examples. Okay, so yes, the first example, once again, would be resource allocation, and now I write the linear program and you interpret it for me, okay? Okay. So let's say I have a linear program like this, and x1 and x2 are the number of Dell computers and Apple computers you can make, right? So what do you want, x1 to be Dell computers or Apple computers? 10 is higher than 5, right? So any sane person will say that Apple is priced higher than Dell, right? So this is the start. X1 is the number of Apple computers you can make, x2 is the number of Dell computers you can make. This is the profit you can make, right? And then how do you want to interpret this? Your interpretation, let's see. So this is not math, this is just real world knowledge. So what do you want, let's say, this constraint to be?
Raw material cost for building.
Sorry?
Raw material cost for building wood.
Which raw material?
Metal.
Okay. Okay, so you have like 20 kgs of metal are required for Apple and 13 kgs of metal are required for Dell, and then you have total 95 kgs of metal. Okay, what about this?
Child labor.
Okay, great. So I see that some people are not fan of Apple computers here. And given such problem, they will only have x2 greater than 0 and x1 equal to 0. But let's say some of us are business minded. So fancy word, manpower for child laborers. Okay, so then it requires 4 human beings, because 1 for making it and 3 for designing the logo on the top, and then 1 for Dell, and then we have 28 people in total to work for us. So if this is the case, this is basically the resource allocation problem, right? How is it different from what you saw in the first class mathematically? Remember what was the first? That was the beer you were supposed to make, right? Like you had 2 kind of dark and light. Can you think of this, making Apple computers and Dell computers, not this linear program? How is it kind of different from that problem, which is going to make a lot of difference as a linear program? So here I would want x1 and x2 to be very good. Okay, so in a sense, the real life problem is not a linear programming problem. Okay, so I am not putting this constraint, so that's why this is almost an approximate version of the problem I wanted to solve. Okay, and the comment I want to make here is that this is not an easy constraint to put. This makes our life very, very difficult. There are integer linear programs, there are just integer programs, and there are a lot of heuristics, but we don't have any nice way to solve integer programs. And actually many of the very difficult problems, as a computer science scientist would call them, NP hard problems, can be formulated as integer programming problems. Okay, so this is the first time which I am telling you. I will probably tell you more. Anytime you have this kind of constraint in your optimization problem, kind of in trouble. We will see in many cases we can still find an approximate solution. This would be one of the applications I will show to you, but in general this makes life difficult. Yes. Yeah, so what you are saying is that you solve this program, your x1 would be, let's say, 13.5, x2 would be 12.1, and you will say that, oh, 13 and 12 is the answer. But what if 14 and 11 was the answer? What you have shown is that 13.5 and 12.1, you get the best solution of this, but it has not shown that the floor is the best possibility. So in that case, your point would be, you would say that, oh, it's at least approximately correct. So whatever is my optimal, you are not far away from it. And this will probably work in this case, but many a times you will have such program and x1 and x2 will just have a choice to be either 0 or 1. And then rounding is going to make a lot of it, right? If your only choice is that, think of this constraint as compared to this constraint. And suddenly rounding does not seem like a great option. And most of these NP hard problems I was talking about, you have this kind of a constraint. Okay, and then does this floor or ceiling, or what we call sometimes rounding, work or not? That's a question in itself. Okay, cool. Okay, so for now we can assume that we can make 13.5 Apple computers or 12.1 Dell computers. Okay, and let's generalize this. What do I mean by generalizing this? You can have, so this is just to take more and more examples of linear program. That's why I'm generalizing this. I can say that I have this rho I as the market cost of so let's say this will index my output. So like in this case I will go from 1 and 2. 1 is Apple, 2 is Dell, and J will be the raw material. Right? It will index the raw material. So then rho I is the price of ith output. Gamma j is the cost of jth raw material. Aij is amount of j needed for 1 unit of I, and Bj is the inventory limit for J. Right? Okay. Can you write the linear program now for the resource allocation problem? Min or max? It's not exactly the resource allocation problem which I had done before. It has one extra thing, right? So take care of it. It's not hard, but yeah. What is extra? Yes. This summation is over. So this is saying use of resource J. So what will come here? Yeah. That's rho I for me. Summation over. Summation over. Correct? Great. Right? This is completely fine. Okay. And now this will be the first example of converting into an equivalent program, which is the simplest thing. I will just say this is Ci. Sounds good? Now you have the same data and it can be interpreted in a totally different way. Okay? What is the problem now? Cost of inventory. Okay? What do I mean by that? Suppose this information is given to you. Okay? And as the manager of the inventory, you want to assign a price to whatever you have. And you want to minimize the total price. Okay? But if you just want to minimize it, you will say, oh, everything is 0. But obviously, if you make the price to be too small, you should be willing to sell it in the market at that price. Okay? You understand? And then the competitor should not have any advantage by buying from you instead of the market. Clear? The minimizing the cost of inventory. Think of it as you are the manager and you want to say that for the other way to say it is for whatever production you want to do, this is the minimum cost I am keeping. This is the minimum inventory cost I am keeping. You want to justify to your boss, why do you have this much inventory? So you are saying that its expected cost is actually the minimum. That's one way to think about it. Okay? So now, if this is the case, can you write the linear program corresponding to this problem? Right? So again, what do you want to do? Objective is to assign cost Yj to each raw material. Right? And when you do it, what will be the cost of your inventory? If Yj is the cost of each raw material of one unit, you want to minimize. Sorry?
AIJ.
No. There is no Aij here. What is the cost of inventory? If one unit, the cost you are assigning as Yj, how much J do you have? Bj, right? Bj, Yj. Okay? Such that, can your cost be less than gamma j? No. If your cost is less than gamma j, then competitor will buy directly the raw material from you instead of from the market. This is not a very interesting constraint. What is the other interesting constraint? What can competitor do? They can buy the raw material from you and build the product I. Right? So what should be the constraint corresponding to that? We should not make sure that we are giving added advantage to the competitor. What should be greater than equal to the? Sorry?
Cost of building one output should be greater than.
Yes, good, good. So what is the mathematics? What is the equation?
Aij, Yj greater than equal to Oi.
Summation over?
J.
Summation over j. And this is there for all the products. Okay? And again, we can do a slightly non-trivial equivalence here. We can say that Zj is Yj minus gamma j. Remember, CI was rho I minus the cost of making product I, right? So this was in some sense the profit. Okay, and even though I haven't formally defined what reduced means, what equivalence means, you are still fine with the substitution. And actually, you should also be fine if I just cancel this term. Because optimizing this is same as optimizing this program with some constant attached to it. Clear? So one step is, yeah, this inventory, value of inventory problem is not that natural, but if you take the leap, then this is the linear program. And so that should be clear to you, but this should be absolutely clear how this and this program are equivalent. In the sense, at this point, I would just say that if I wanted to solve this instead, I will just solve this. And the advantage is that this is much closer to the standard form than before, right? Gamma j is the market price, and yj is the actual price which you suppose for you what is the cost of the material, right? So you want to say that, oh, even in the market it is 10 rupees per, but for me its value is 12 rupees or something. So that's why there are two different. Yj is the variable, gamma j is the fixed market cost. Does that answer your question? Okay. And now you saw same data but two different linear programs. Okay, and to now advertise this course, in few weeks you will see that what it means is that the best possible profit you can make is going to be equal to the minimum possible cost of your inventory. And I'm sure at this point you don't see it, right? This seems like two different problems, but this is in some sense the power of linear program. We will see that how this optimization problem and this optimization problem are intrinsically related. And we will mathematically be able to prove that yes, the maximum profit you can make should in some sense be equal to the imagined cost of my inventory. And this will be shown but in few weeks. And again, if someone asks me, this is my favorite concept and I will keep highlighting it, and you will see the power of duality again and again in this course.